Hi guys, welcome to the Geography Academy. My name is Brian. This video is for the Cambridge International GCSE, but if you're not doing that exam, you still might find some interesting facts here. The topic of today's video is from the Natural Environment section of the course, and it's about volcanoes and earthquakes. Now this is a long video, but it's split up into several sections, and you can see that in the description below. If you're looking for more help or advice on the course on how to get an A, visit thegeographyacademy.com. We've got loads of resources there and lots of things that will help you out. So let's jump straight into it. First of all, you're going to need some simple definitions to understand some of the earlier content. So let's begin by looking at what an earthquake is. Now, most of us have heard about this in the news as the ground shaking. But what's actually happened is that there's been a fracture in the Earth's lithosphere, which is the crust around the mantle. It's the rock that we live on. And there's motion here, and this causes seismic waves. A volcano then is a fissure or a vent in the Earth's surface that is conducted to the Earth's interior. And it often looks like this on the left, where we can see some big smoke coming out of it, and it will emit lava, gas, and other volcanic material. So that's coming from all that kind of hot magma that we have underneath this area here. So that's really all the vocabulary you need for volcanoes and earthquakes for now, and we're going to go into those in a bit more detail a little later. But first we want to figure out how these are formed. So let's have a look here at the Earth's structure. Now, the Earth was formed by many great masses coming together, and as it did, it caused a great heat. So this heat is usually found in the mantle and all the way down into our core. So the core radiates a huge amount of energy, and it is solid. And there's also a lot of radioactive material that is decaying over time, which releases a high amount of energy. So in our core, there's a lot of heat being released. So in our mantle then, we've got molten rock, which is in motion around this area here. And at the top then we have our lithosphere, as we mentioned before, which is the crust, which is where all the mountains and the land and all life is. And then the asthenosphere is this area between the mantle and the lithosphere. This is, as I mentioned, is not to scale, but usually the lithosphere is compared to a piece of paper over a football. So it's very, very, very thin in comparison to the great depth inside the mantle and inside the core. So our lithosphere is actually broken up into many different plates. It's not one solid piece, and it's continuously changing. So this is, for instance, shows all the active volcanoes around the world, and it shows them on the edges of different plates. So it's crucial to understand how these plates interact with each other to understand the distribution of earthquakes and volcanoes. It's important to point out as well that we have two types of crust. We have the oceanic crust and we have a continental crust. The continental crust is thicker and less dense and older, and the oceanic crust is thinner and denser, meaning that it's heavier. So keep that in mind and make sure you have all that information down before moving on. So looking at this diagram on the left, we see that there is a heat source at the bottom, and that heat source is causing the liquid in the bowl to rotate. So as it heats up, it rises, it begins to cool down as it reaches the furthest distance from the heat source. As it cools down, it then begins to sink, and so on. This happens in the mantle, the same as it would in a kettle, where the heat from the core is heating up the mantle. So all the hot material will start to rise, and as it begins to rise, it will then cool as it meets the lithosphere. And along that area of the asthenosphere, then it will cause an area of friction to build up. So the thermally driven convection currents are the most important factor in plate tectonics. This is the actual driving force behind the plate's movement. So entire continents are moving apart from each other or into each other every moment. Now they move relatively slow, about maybe a half a centimeter up to about 10 centimeters per year at maximum. But this happens all over the world. So earlier we talked about how the plates are divided up into little shells. So two separate plates could be moving apart from each other, such as the Eurasian plate and the North American plate. We see that America is moving further away from Europe every year. When you're explaining any of the plate tectonic boundaries, it's incredibly important that you mention this idea of convection currents each time you go to answer a question, and it'll get you lots of extra marks. So speaking of plate boundaries, moving on to our first one, we're going to discuss a constructive plate boundary. Also, you might see it written as divergent plate boundary sometimes. So let's focus on this little area here. So we said that the heat from the inner core is pushing the magma, it's rising, it starts to cool, it might start to become more solid and cause friction. So both these plates then are being dragged in opposite directions. So as the plates are actually being dragged apart, the magma is able to rise through the middle and might be able to form new land. So we can see here two of the oceanic plates, and they're both moving apart from each other because of convection currents. So as the plates separate, then a gap opens up and we see the rise of magma through that gap there. So the molten magma, when it reaches the surface, is known as lava, and that will begin to cool and to form hard rock. So when it forms hard rock, then it occupies the gaps that is available, and let's just say this becomes our first layer there of new rock. It's a brand new rock, brand new land, which is why we call it a constructive plate boundary, because it builds off of what was there before. Now, if we were to see what happened later down the line, well, convection currents continue to move and the same process will happen again. So now that new land that was created first is being separated. So there it is as one and one. That one's been split now, and we get new magma occupying this area all the way up here, and that will form a new land, which we'll just write there as number 2. And this process of the land continuing to be created and continuing to occupy this space as the convection currents are going out is known as ridge push, because this actually helps the plate move. So as it's forcing all the magma in there and the rock is hardening, it starts to go down and starts to push the ridge and helps the convection currents move it. So like I mentioned before, magma rises through the gaps and it hardens. Oftentimes if this happens like in the mid-Atlantic ridge, in the middle of the Atlantic Ocean, you'll find that the pressure and the cool temperatures will help harden the rock much faster as the lava tries to come out here. This is known as pillow lava, and you can see that these eruptions can be quite deadly when they're over water. So that's our first plate boundary, a constructive plate boundary. What I actually recommend is that you stop at this section and that you make a quick little profile for a constructive plate boundary. You draw a diagram and just explain it beside the diagram, and then you can continue on after that. So our next plate boundary that we're going to discuss is a destructive plate boundary. Now, a lot of the similar things are happening. For instance, we have convection currents at work here. Remember that we have two types of crust or plates. We've got a continental crust, which is thicker but less dense and older in general. And then our oceanic plate is going to be denser, heavier, and usually contains things like basalt rock. So what happens in a destructive plate boundary, you can see on the left hand side here, is two plates are moving towards each other. So they're going to come in contact, and as this occurs, the denser oceanic plate is going to be driven underneath that less dense continental plate. So that kind of sits on top of it as this plate begins to go down. This is known as subduction, when the oceanic plate is going underneath the continental plate. There's also another effect here, and that is slab pull. So as the oceanic plate is moving into the continental plate and being subducted, the weight of the plate that is being subducted begins to actually have a pulling effect on the rest of the plate and helps the convection currents and the ridge push at work to actually cause this motion to happen. So looking at the bigger diagram here, we know that ridge push will be happening here at the constructive plate boundary, and we've got the convection currents in the middle And then on the other side where we see the destructive plate boundary, we have slab pull in action too. So in these areas, the oceanic crust, you're going to find that as the oceanic crust is going down, it has a lot of life forms that have settled onto the top of the crust. And as they are being subducted, they begin to melt with the heat in the asthenosphere. And everything begins to rise up with that heat as this crust is being melted. So the heat then rises through the continental crust and will leave volcanoes in a chain along the continent. So let's take a quick look at where this may happen. If we look down here in the South American plate, we'll see the Nazca plate is behind it. The Nazca plate is an oceanic plate that's moving towards the South American plate, and the South American plate is moving towards the Nazca plate, and it is a continental plate. So this is a destructive plate boundary. Along this area, just like in the diagram, what's happening is as the Nazca plate moves towards the continental plate, the oceanic crust is being subducted, and this is causing a chain of volcanoes all along the Andes Mountains. So this will give you an idea. These are all the volcanic zones along South America, and you can see here that they form this arc. And this is known as a volcanic arc, where volcanoes appear in the same area along the same place over land. Over on the other side of the Pacific Ocean, we see that, well, this is part of the Ring of Fire because of all the volcanic activity that goes on in this area. But over on the other side, we can see that the Pacific plate is moving out and up towards the Eurasian plate, and the Eurasian plate is moving towards the Pacific plate. In this region here, it's also caught within other plates too. We find the islands of Japan. Now this is slightly different because when the oceanic crust begins to subduct and then begins to melt and all the materials begin to rise, then we see the formation of volcanoes within the ocean. So these are known as island arcs. The third plate boundary that we want to look at is the conservative plate boundary. On the left, you'll notice a map that shows all the active volcanoes in the world. So notice how they're dispersed along the mid-Atlantic ridge like we talked about, and there's many going along the Pacific Ocean. And on the right-hand side, you'll see a map just showing all the earthquake activity. Now, one thing you might notice is there's far more earthquake activity than volcanic activity. And that's because volcanoes and earthquakes, although they will happen in the same areas, there are many areas that have earthquakes with no volcanoes. And these are often found in conservative plate boundaries. So what's going on at a conservative plate boundary? Well, before we were looking at two plates that were moving away from each other, and we also looked at plates that were moving towards each other. In a conservative plate boundary, the plates might be moving in opposite directions, or they may be moving in the same direction but at different speed. During that change in speed or alternate directions, there are not going to be straight flat lines in which two plates can slide past each other smoothly like this diagram might show, but in fact there'll be a lot of friction that builds up by the plates getting trapped. So when they're trapped and the two plates are trying to move, this tension builds up. Eventually that tension will be released, and this has the potential to unleash massive earthquakes. So that is the conservative plate boundary. Nothing's destroyed, nothing's created, but it can cause enormous earthquakes. So a quick test for you now. Having a look at the map on your left, can you give me examples of two plates that cause a constructive plate boundary, two plates that cause a destructive plate boundary, and two that cause a conservative plate boundaries? Pause the video, look at the map, and see if you get the answers right. Okay, so here are some answers for you. So we can see that we'll find a constructive plate boundary between the North American and Eurasian plate. We'll find a destructive plate boundary between the Nazca plate and the South American plate. And we might find a conservative boundary between the North American plate and the Pacific. So there you have it. That's the 3 plate boundaries that you need to know for your exam. I would suggest stopping here, making a profile for each of them, making sure you have examples as well to use if you do have to explain them. Next, we're going to go over more specifics about volcanoes and earthquakes and also go into some case studies. But always remember, when it comes to case studies, you want to do a bit of extra research yourself and just double check that the facts are up to date. Go. Okay, this is a basic diagram of a volcano, so let's have a look at the structure. Down at the bottom, along here, we have got the magma chamber. And then through the magma chamber, magma will rise up through the main vent and will eventually lead to the top of the surface, which is known as the crater. There, so we have main vent and we have the crater. Now, what's coming out of there is magma. But when it reaches the surface and begins to flow down the side of the mountain, which is pretty iconic of an active volcano, we will call this magma will be lava. So inside the volcano, magma, see there, and outside the volcano, known as lava. Alright, now you might notice here that we've got different line structures going through the volcano. So these are just layers of lava that have hardened over the years, and also layers of ash cloud, because we don't always get volcanic eruptions, but sometimes we might just get ash cloud. Put that in there. Alright, so those are the basics there. We mentioned before as well that the rock will harden when it comes up to the surface and begins to slow down, and it loses its heat source, will harden into volcanic rock, and that's what forms the whole volcano as a mountain. So this just builds up over the years into different tiers. So we could have something like the first stage of the volcano is here, and then later it moved out and became a little bit bigger, and so on, and will continue to grow as long as it's active. So there are different types of eruptions that may happen. You might get a pyroclastic flow, and this is when larger chunks of the mountain will come off and we'll get pyroclasts, which are a combination of dust and rock moving down with super hot gas under the power of gravity, basically. So we'll see that kind of happening maybe on the side of the mountain, as it looks like an ash cloud, but it moves very fast and it just follows the mountain all the way down. So these can be really, really fast and really deadly. The other thing that we might see in terms of an eruption is for a lahar to happen. This is basically the mixture of volcanic debris, like the pyroclast, mixing with any kind of source of water. So there might be heavy rainfall, there might be surface flow over the mountain, or there might be a river or a stream. So the debris gets into that water source and then it magnifies the volume of the water and sends it rushing down. So as you can imagine, this can be very, very quick also. Viscosity is going to decide the shape of a volcano. If you have high viscosity, it will look something like this one on the right, like honey. It will be very hard for the liquid or the fluid to lose its shape. And if it's very low in viscosity, it will move more like water and it will be very fast and easy to lose its shape. A shield volcano is formed with lava that has very, very low viscosity. This means that as the volcano erupts, the lava is able to move more fluidly and over a greater distance. What this leaves us with is something like the volcanoes that we would find in the Hawaii Islands, USA, where they're very, very long mountains, but not very high mountains. If you were to take a helicopter around or see a side profile like this, you would think that it looked like a shield placed on the ground. The second type of volcano to look at is a composite or stratovolcano. It's a typical volcano. We looked at it just a moment ago with the diagram, and an example of this is Mount Fuji. Now, in its side profile, we can see that it's much more steeper, and this is because the lava will be of a very high viscosity. So as the lava erupts out of the top, it won't make it too far before it solidifies and becomes solid rock. So this continues to allow the mountain to grow in such a high angle. Another type of volcano you might come across is a caldera volcano. Now this volcano, it had very, very high viscosity, so high in fact that the mountain grew too tall for itself, and then it would have the top would have exploded off during an eruption. In this case now we see the outer edges here of the Caldera volcano is actually the original wall of the volcano, and this has since been blown off, and now a new volcano begins to grow inside the crater lake here. An example of this one here is Mount Rinjani in Indonesia. Okay, so for your earthquakes and volcanoes, you need a case study of a volcanic eruption. Now, maybe you studied something different in your school. If you did, this is just going to help us, maybe a comparative. And if you already have a case study, great. And like I said before, it's really good for you to do some extra research on your own case studies as well. But here's some basic information about this one. The case study we're going to talk about is the Icelandic Eyjafjallajökull. So that is the best pronunciation I can do of that to do it any justice. However, I know from talking to Icelandic people that's not exactly how you pronunciate that. However, this area we saw an eruption during 2010 on April 15th. So let's have a look into that. First of all, for each of your case studies, you want to know the location. So we can see here that Iceland is located up here in Europe, and it is running, well, the mid-Atlantic ridge is running straight through Iceland. So that is between the Eurasian plate and the North American plate that are moving apart, meaning that it is sitting on a constructive plate boundary. Now, when this eruption happened, there was huge sheets of ice that were over the volcano. So when it erupted, all the water mixed with all the volcanic debris, and it lifted it up into this massive ash cloud, also known as telfra. As we can see down here from the Met Office GIF, that they're showing the extent to which that ash cloud moved over Europe. So that was because the prevailing wind just happened to be moving in that direction, and it blew all the ash towards Europe. So when this volcanic eruption happened, it didn't just impact Iceland, it impacted a much, much greater area. The short-term effects on people. In Iceland, we saw that immediate evacuations were made in the run-up to this volcanic eruption. So there are telltale signs that there could be a volcanic eruption, and it's up to the Iceland Meteorological Office and National Emergency Agency to help evacuate people. There was a loss of livestock due to ash inhalation, and there were many farms completely destroyed. Outside of Iceland, this volcano impacted much more people. 95,000 flights were delayed, and we coined the term volcanic refugee. Most of these were coming in or out of airports of Western Europe countries, and in the stock market, a lot of these air travel agencies dropped by about 4%. So there was many people who were stranded at the airport who could not go home, and there was many people who were just about to go on holidays and who were not able to leave their country. The effects on the environment were quite high in Iceland. Huge amounts of glacier ice melted, which are incredibly important for many different reasons to the local environment and the global environment. But afterwards we found that this melt water continued to increase at a higher rate. Floods then were created by all this ice melt, and also to add to that, we had lots of telfra and other volcanic materials in the water too. Outside of Iceland, one of the biggest environmental problems was dealing with organic waste. So because the transport routes were closed to so many places, a lot of food that had been grown purposely in order to actually be consumed at that time didn't get to where it was supposed to go. So because of that, lots of food got put to waste and was dumped. About 150 tons of CO2 was released per day by the volcano. Now, you should have a fair idea of the negative impact that CO2 can have on the environment. However, one of the interesting things was because they had grounded so many flights, we actually prevented millions of tons of CO2 being emitted into the atmosphere every day. So in that sense, the effects of the volcano could have been a positive one. Long-term effects. In Iceland, we saw that a lot of settled ash increased overall glacial melt. This is because the ash is much darker than the ice and is able to absorb more incoming solar radiation. People found that they had lots of respiratory problems long after the event occurred because of remaining ash. Outside of Iceland then, a lot of companies had to bear the cost of this natural disaster, roughly about 2.8 billion in insurance and trade losses. For an example, Kenya estimated that they lost over 3 million through cancelled trades in this one event alone. Opportunities for people, was there some positives? Well, in Iceland, people were also spending more time there, and in the future, tourism increased as Iceland was all over the news and newspapers and on loads of videos for a long period of time, which increased people's awareness of the country. So they have seen an increase in tourism since then. Outside of Iceland, then, the transport links that weren't based around airplanes increased. So use of the Eurostar, lots of trains and ferries all over Europe were used immediately and were very, very full for that time period. There was also a lot more trust put into these transport methods after this, so a lot of people began to use them more in general. Increase spending by tourists that were stranded. So even people who had to go to an airport to fly out of their own country was left stranded in that city. Or it's possible that they could have been abroad in another country and would have had to come back into a city or a town to get some accommodation and wait until the next flight. This took a long time for many people. Overall though, not just in Iceland but on a global basis, lots of people live around volcanoes. And for many of us that don't, we wonder, why would you? Here are a couple of reasons why people would live near volcanoes. First of all, soil fertility. So if the eruption has happened quite a long time ago, the soil can benefit from the nutrients of all the ash telford that's dropped. You also are close to geothermal energy, which a lot of countries that are volcanically active are able to access quite easily. Hot springs then are really good, as a lot of locals will tend to use them and this becomes a part of their tradition, or it's used to increase the tourism to that area. New land is created, so like the example we used of Hawaii, there's an area that its land is extending very, very quickly after all their volcanic eruptions. Sulfur mining and rare mineral mining are much easier if you're close to the source where these things are being created, and they're tourism then. Lots of people will go hiking or adventure tourism, or they just want to see a real volcano in person. You've got things like geography school trips, or you have other extreme sports like downhill mountain biking on a volcano. Traditions. So if you have a culture that has grown up on a volcanic island, maybe they were well established before there was any volcanic activity, or at least they were established during a period where there was less volcanic activity. In these conditions, then, you would see that people are very used to living under the foothill of a potential erupting volcano. Also, with the development of science and technology, volcanologists and geologists are able to monitor volcanoes very closely and are able to predict eruptions quite well. Earthquakes then, a couple of words that you need to know. An earthquake happens at the focus. So before we were talking about a conservative plate boundary and how friction is built up and then released. So this friction builds up and it's released in an area called the focus. The areas that have the two plates either side is known as the fault line, or a crack or a fault in the tectonic plate. And directly above the focus we find our epicenter. So oftentimes you'll hear it recorded the epicenter of the earthquake was in a certain place. This is the strongest point at the surface from the earthquake. Now that doesn't necessarily mean that it had the greatest impact there. It depends what's on the surface for that. So seismic waves are sent out. The measurement of an earthquake can be done in two ways. You can measure it on the Richter scale, or you can measure it on the Mercalli scale. If you measure it on the Richter scale, know that it's a logarithmic scale, meaning that, for example, 6.0 is 10 times more stronger than 5.0. 7.0 is 10 times stronger than 6.0. The Mercalli scale then is measuring things like the damage that was done to monitor the severity of the earthquake. It's not the same as the measurement of magnitude that the Richter scale measures. The case study for the earthquake that I've chosen is Nepal, April 2015. Again, if you haven't actually studied this case study, it might add as a good alternative and comparative. The earthquake was measured at a 7.8 on the Richter scale. However, it's also measured in some places as 7.9. It was caused because of a sudden thrust along the main fault line where the Indian plate meets the Eurasian plate. So this was an enormous earthquake, and what can happen a lot of times is once there's a thrust, it takes a while for the plate to actually settle into place. So as it does so, we experience aftershocks, which are also big earthquakes. So when you've got something like a 7.8 earthquake, you can get enormous aftershocks. A 6.8 earthquake is above the average earthquake, and as an aftershock, that is enormous. The devastation was widespread throughout Nepal because it is a low-income country, or an LIC. A lot of the buildings are not able to cope with such an earthquake. A lot of the infrastructure is quite a low standard in this landlocked country, and it is a very mountainous region, which means its natural environment is difficult to get help to. The effects on people and the environment. Around 600,000 homes were destroyed and more than 288,000 were damaged. And this was only in the 14 worst hit districts. Estimated around 1.7 million children were homeless. Enormous landslides and avalanches happened. So in such a mountainous region, you are going to get a high number of landslides and avalanches, but the earthquake was able to trigger a lot of these to happen in the immediate aftermath of the earthquake and the aftershocks. Because there was such an impact over the building structures and the facilities, a lot of the water became contaminated. A lot of chemicals and debris mixed with the water, and even though a lot of this can be washed away through several seasons, a lot of it also goes into the soil and into the groundwater. So it's going to be a very, very long-term impact there. So you can see on the right-hand side there, the deaths in total were around 8,000 in Nepal, and also in surrounding countries that border Nepal was quite high too. Injuries were very, very high, into several thousands. This is taken from Wikipedia, and got up to 23,000. So that's an enormous death toll and a huge injury toll to happen there. Obviously, the size of the earthquake had a big role to play in it, but also the development of the country. Some of the long-term effects then, reconstruction up to 9 billion. A lot of people were in mountainous areas, so this means they will be the slowest to recover, but also were the slowest to get help at the time. So they had far more worse short-term effects and long-term effects. Tourism is one of the biggest revenues for Nepal. It does a lot of mountain tourism, very famous for its Everest peak climb and other climb in the Himalayas, and many people get their jobs from guest houses or as guides, the Sherpas, and a lot of infrastructures like their airports depend on the money they received from tourists. So this was obviously impacted for a short time, but actually recovered eventually. An increase in glacial lake outburst floods. Because there was the shaking and the cracking, there was a weakening of the ice, which caused a lot of glaciers to melt easier. About 2% of the forest cover was affected in the area and was completely lost. So the forest acts in two ways to help this landscape and these people. It helps by absorbing water that comes in during the rainy season and prevents flooding, and also it prevents against landslides and soil erosion. So taking 2.2% of the forest then caused lots of different types of natural disasters to happen further down the line, such as landslides or such as floods. The other long-term effects we saw were other earthquakes and aftershocks that went on for a long time afterwards. Each of them were very, very dangerous. Even with buildings that were safe to go back into, many people didn't feel secure because of the aftershocks and also acted like homeless people. How to reduce the impacts of these natural disasters? There's three main ways: we can predict, we can prevent, and we can respond. So looking at earthquakes first, how can we predict an earthquake? Well, actually we can't. We're not able to predict the exact time that an earthquake might strike. However, even if you're looking down at this map, we can monitor earthquakes, we can measure magnitudes, we can understand that tectonic plates are moving in a certain direction, so we can anticipate that there could be big eruptions coming. Now, one method is to see how much the plates are moving, or if there seems to be any friction or buildup, or sometimes there's a routine where we see large earthquakes every, say, once every 100 years. So we can anticipate that. Nepal in 2015, for example, was highly anticipated that there would be a large earthquake in the coming years leading up to 2015 in the Kathmandu area, and it was predicted to cause a lot of devastation. This ended up being true. Prevention is something that can be done in earthquakes, but it is hard in terms of the larger scale earthquakes. So we cannot stop an earthquake, but we can prevent loss of life, damage to infrastructure, and the environments. Protection against secondary disasters is also possible, such as landslides, rockfalls, and glacial lake outburst floods. This we can do by having the right preventative methods. For example, with landslides or rockfalls, we can put in more security on the slopes to make sure that they don't succumb to the pressure, and we can also make sure that we don't build in environments that are directly beneath these potential disasters. When we look at the Nepal earthquake in 2015, one of the worst parts was the infrastructure damage. It left a lot of people homeless and a lot of buildings collapsed on people, causing deaths. In countries such as Japan, buildings have to be built in certain requirements to prevent against them collapsing during earthquake. One way to do this is to have very, very deep foundations of the building. The other is to allow the structure to some flexibility in order for it to move with the seismic waves. There are also other inventions out there to help prevent against loss of life. In certain earthquakes, such as the one in Bam, we saw that many people died at nighttime in their homes because the houses collapsed on them. So recently we've created beds that under seismic activity collapse into a safe box that will also have things like water and food prepared. So if an earthquake strikes during the night, you will be wrapped tight in your box and well protected, and you will have stores of oxygen, water, and food to keep you alive for many days. The response to earthquakes then can be absolutely crucial. We might get these responses through rescue teams at the very initial stages. We need to get them in there and get people who are trapped to safety. You can have long-term and short-term infrastructure solutions such as roads, helicopters, and things like that can get to areas where people maybe aren't able to get to. You also need places like when we had the Nepal earthquake, you need places for people to actually live for a while. And this could end up being a long-term housing facility because people might not be able to build that quickly. International aid from other countries, NGOs, non-government organizations might also send aid. So this could be in the form of things like food, shelters, you could get water, you can get professionals like doctors to come into the area or search teams. This is particularly difficult with long-term recovery as places like LICs, low-income countries then are not able to get all the aid from places like NGOs, from charities for a long period of time, and other natural disasters may happen around the world that actually take a lot of the organization's resources too. In Nepal, they got a huge response from loads of countries all around the world. Here are just a couple of examples, but you can go on and research some more. India had a huge impact in terms of the aid effort brought to Nepal, bringing thousands of tents and blankets to those in need. They had their Air Force evacuate many Indian citizens and foreign nationals, and also carry loads of aid and professionals into the country to help with the relief effort. Even smaller nations who don't have a close tie to Nepal, such as Ireland and South Korea, sent up to $1 million in aid immediately to them. Countries like Canada then sent a disaster assistance response team, or the DART. This was 30 highly trained professionals to help organize the relief effort on the ground and also send millions of dollars and supplies there. China sent an international search and rescue team with professional rescue dogs and also $3 million in US dollars. And Bangladesh, although wasn't able to give millions and millions of US dollars, did send tons of food, simple foods like rice and bottled water to help out there. So there was a huge relief effort of this particular natural disaster, and this really helped Nepal. So volcanoes are a little different. Volcanoes can be predicted, but to a certain degree. There's definitely some volcanoes that erupt very quickly and can erupt more violently than expected. It's hard to know how long and how violent the eruptions are going to be. We can measure the seismic activity, the shaking in the ground, as we'll find that there's a lot of changes on the lead up to a volcanic eruption as the magma is trying to make its way up to the surface. we can often find that a lot of gas is released, such as large quantities of sulfur released into the atmosphere. The water in the area could be impacted, changing its chemical composure and also heating up. And we might see physical changes to the structure of the volcano itself. So this means that it might actually move and it might change its height. In the Icelandic eruption of 2010, we saw that it was well predicted ahead of time. Up to 11 weeks before, the volcanologists and geologists in the area were monitoring changes in the volcano's shape, about 15 centimeters over an 11-week period. This is clear indications that this eruption was going to happen, and it was going to happen very, very soon. Also, the scientists in the area have carefully studied the secondary impacts, and they're educating locals, making sure that everybody knows what will happen once this volcano erupts, or at least the possibilities. The prevention then is something similar to earthquakes. You can prepare survival kits, you can have evacuation routes and early warnings. Unlike earthquakes, you can have early warnings. You can also educate the locals and let them know what to do in this event and what the secondary impacts might be, not just to be running away from the volcano, but to make sure that they look out for things like lahars. You can also channel lava flow to a certain extent and to help force the lava in certain directions. The prevention used in Iceland, the Icelandic Meteorological Office were the main group that were overseeing the monitoring and making sure all the scientific data was being received by the government. And then the Department of Civil Protection and Emergency Management let everybody know what was about to happen and how to evacuate and avail of any of the help. The response then, there wasn't such a large response needed. They had a lot of volunteer staff, and they had 700 people evacuated, and 200 of these people needed temporary shelters and refuge, and the rest were able to take shelter with friends and families. But oftentimes the impacts can be worse. You might need entire rescue teams, you might need long-term aid, you might need money and loans from international organizations or from other countries, and it can often be difficult to recover, just like in the case of earthquake. So that's the end of this video. I hope that's useful for you, and that if you have any further questions, that you go to the geographyacademy.com. So here you can go to the IGCSE section and see what's available there to help you out this year. Thanks a lot for listening, guys. Any more questions, leave them in the comments, and of course subscribe, so we'll be encouraged to make more of these videos.